Hello everyone. Now we have a question which says there are two columns, list 1 and list 2, and we have to match these complexes in list 1 with the statements in list 2. So let's analyze these complexes one by one, and then we will see the statements that correspond with each of these complexes. So A, we have a cobalt complex, COH2O, whole 6, 2 plus. And if we look at the statements, it is regarding the magnetic moment and the magnetic character and also the shape of the complexes. So A has cobalt. Cobalt is the central metal ion and the oxidation state of cobalt here is +2 because H2O aqua ligand has 0 charge. Now the ground state electronic configuration of cobalt is 3d7,4s2. And in the +2 oxidation state, the electronic configuration becomes 3d7,4s0. Now, what kind of ligand is H2O? So, H2O here, it is a weak field ligand. And thus, we have a high spin complex. And since we have 6 ligands, 6 aqua ligands, so this complex is obviously an octahedral complex. Okay. Now, we accommodate these 7 electrons in the T2G and EG orbitals in the high spin condition. So first these will be singly occupied. So 3 plus 2, 5. And then there will be pairing in the T2G orbital 5, 6 and 7. Now we know that when unsymmetrical filling of T2G happens, that means we have this orbital contribution to the magnetic moment. So because of this unsymmetrical filling of T2G orbital, there is mu orbital contribution. That is, the magnetic moment has orbital contribution, and that is why the total or effective magnetic moment is greater than the spin magnetic moment. Okay. And also this unsymmetrical filling of T2G will give rise to one more consequence, that is a weak Jahn-Teller distortion. So for this cobalt complex, which has an unsymmetrical electron filling in the T2G orbital, that will give rise to mu or orbital contribution to the magnetic moment, which results into the total magnetic moment or effective magnetic moment being greater than the spin only magnetic moment, and also the weak Jahn-Teller distortion because of the unsymmetrical filling of the T2G orbital. So if you could find these things from the statement, then statement 1 says magnetic moment higher than spin only value and weak JT distortion. Statement 2 is spin only magnetic moment and absence of JT distortion. No, we have a JT distortion which is weak for this cobalt complex. So second will not be an option. Then paramagnetic and tetrahedral, no. Diamagnetic and tetrahedral, no, because this complex is octahedral. So second, third and fourth options will not be correct for cobalt complex A. So the statement magnetic moment higher than spin only value and weak Jahn-Teller distortion is the correct option for A. So A will correspond to statement 1. Okay, now moving on to the complex B, which is a chromium complex CrH2O whole 6, 3 plus. So the central metal ion is chromium, and as you can see, chromium is in the +3 oxidation state. So chromium, we know the valence electronic configuration in the ground state is 3d5,4s1. So ground state, it is 3d5,4s1 in the ground state. Okay, now in the +3 oxidation state, the valence electronic configuration becomes 3d3,4s0. Okay, so now if we try to fill these 3 electrons, so it has a D3 configuration. So that will be filled in the T2G orbital, 1 orbital, 1 electron. Okay, so T2G3. Now you can see that T2G3 means the T2G orbital is symmetrically filled, evenly filled. And because of this symmetrical filling, there will not be any Jahn-Teller distortion. And what else? No Jahn-Teller distortion because of the symmetrical filling of the T2G orbital, as well as there won't be any difference in the mu effective and mu spin only, because mu effective will only be higher than mu spin when there is orbital contribution, that we know. But here the T2G orbital is symmetrically filled, okay, and that is why the effective magnetic moment will also be the spin only magnetic moment. So mu effective is equal to mu spin. No change in the total magnetic moment. It will be equal to mu spin because the T2G orbital is symmetrically filled. Now let us see if we have any statement near to this conclusion. Yes, spin only magnetic moment and absence of JT distortion. Yes, the second statement says the complex has only spin only magnetic moment and there is no Jahn-Teller distortion. So our complex B will belong to statement 2. I hope you are following how we are getting these answers. Okay, now if you look at C and D, so you in the complex C and D, the nickel and the palladium complex, you can see there are 4 ligands. So 4 ligands means the structure will be either square planar or tetrahedral. So we have third and fourth options which say tetrahedral structures. So C and D will either be third or the fourth statement. Okay. And now we have only to identify that whether the complexes C and D are paramagnetic or diamagnetic. Okay, so the complex C has nickel as the central metal ion, and we know that nickel is 3D8,4S2 in the ground state. And chloro, in this complex, chloro has a -1 charge and PPh3 has 0 charge. So the oxidation state of nickel will be +2. So nickel is +2 oxidized. So in the +2 oxidation state, the valence electronic configuration becomes 3D8,4S0. Now you have to see the nature of ligands with which this nickel is coordinated. Now we have 2 Cl ligands. So Cl ligands, we know that these are weak field ligands, okay? While PPh3, triphenyl phosphine, is a strong field ligand. Now, if we have an equal number of 2 different types of ligands, the overall effect will be somewhere intermediate or borderline. That is, mostly the overall effect will be of the weak field ligands. That is why we expect this to be a high spin complex. Also, you can see that we have the option of a tetrahedral complex for both of these C and D complexes. Now, if C is tetrahedral, so what should be the reason why this is tetrahedral and why it is a high spin complex? That also should be a question. So if you look at the ligands here, so we have 2 chloroligands and 2 triphenyl phosphine ligands. Now this triphenyl phosphine ligand is a bulky ligand, and because of the presence of a bulky ligand, because there are 3 phenyl rings, okay, so that is why, because of the presence of this bulky ligand, the complex attains a tetrahedral structure, because in a tetrahedral structure the ligands will be around 109 degrees apart, while in a square planar structure these will be 90 degrees apart. So that is why this complex prefers a tetrahedral structure in order to avoid steric overcrowding of the bulky triphenyl phosphine ligands. And we know very well that tetrahedral complexes are mostly high spin complexes. There is less possibility of getting paired, and this is the reason why the combined effect of 2 weak field and 2 strong field ligands comes out to be an intermediate or a borderline effect. leading to the high spin complex. So this is an important thing to understand in this complex of nickel. So now if we fill the 8 electrons here, so even if it is a strong field or weak field, we know that whenever we fill this 8 ligands, then what will happen? 1, 2, 3, 4, 5, 6, 7, and 8. So as you know, this is the crystal field splitting arrangement of the d orbitals in the tetrahedral geometry, whereby the d orbitals are split into low energy E and high energy T orbitals. And we fill the 8 electrons, whereby we can see here that E orbital is completely occupied while T orbital has 2 unpaired electrons. And the presence of these 2 unpaired electrons makes this nickel complex a paramagnetic complex. So the characteristic of this nickel complex is tetrahedral geometry and paramagnetic character. And now if we go back to the question, so we have this option 3 as paramagnetic and tetrahedral. Now we know that this perfectly fits the nickel complex, paramagnetic and tetrahedral. So C corresponds to option 3. So this complex C corresponds to the statement 3. Okay. Now coming to complex D, which is a palladium complex. We know very well that palladium is in the second transition series and the valence electronic configuration should be 4d8,5s2. But actually these s electrons, they move into d orbital forming 4d10,5s0. Okay. So we have a 4d10 configuration for palladium. Now, we know very well that triphenyl phosphine PPh3 is a strong field ligand and it has a 0 charge. And that is why the d electrons will be paired. In any case, whether paired or not paired, we have a d10 configuration, and that is interesting that all the d electrons are complete, and that is why the d orbitals will be completely filled. So we have a complete saturated d orbital situation. So we have 10 d electrons and all the E and T2G, all the d orbitals are completely filled. Since they are completely filled, there is no unpaired electron, and that is why this complex is diamagnetic. Okay, diamagnetic and tetrahedral. And that is why we have this one statement left, that is statement 4, diamagnetic and tetrahedral. So D will correspond to statement 4. So D, our complex D, corresponds to statement 4, diamagnetic and tetrahedral. So C3D4, then B2A1. That means 1, 2, 3, 4 serially for ABCD. So we have this option. Yes, it's in the second option, A1, B2, C3, D4. So this option number 2 will be our correct answer. So I hope you understood the explanation for this question. We have to just identify the valence electronic configuration, the oxidation state of the central metal ion, and then we accommodate these electrons, the d electrons, in the T2G and Eg orbitals for octahedral complexes and T2 and E orbitals for tetrahedral complexes. And depending upon the filling of electrons in these orbitals, we decide that whether it is paramagnetic or diamagnetic, whether it will show Jahn-Teller distortion or not, and whether there will be orbital contribution to the magnetic moment for these complexes. So I hope this explanation was clear enough. If my videos are helpful to you, please like, share and subscribe, and please let me know what you want to learn next in chemistry in the comment section. Thank you so much.